In this section, we're going to study two tests, the ratio and the root test, and those tests are going to help us to determine whether a given series is absolutely convergent. The first one, the ratio test, here's the statement. So it says the following: if the limit as n goes to infinity of the absolute value of this quotient, and what's this quotient? It's the n plus first term of the sequence divided by the nth term of the sequence. So if the limit of the absolute value of this quotient is smaller than 1, then what this theorem is telling us, then the series is going to be an absolutely convergent series. And remember that from the previous section that every absolutely convergent series is actually convergent. So we get this for free in some sense. Okay. And the second one, the second part of this test, it says if the limit as n goes to infinity of the absolute value of the same quotient now is bigger than 1, if this happens, then the series must be a divergent one. Okay. All right. The only missing case is when the limit of the absolute value of such a quotient is equal to 1, and that's left as a comment after we finish the proof of the theorem. All right, let's start by proving it. So proof. Okay. So what do we have? We have that the limit of the absolute value of this quotient is smaller than 1. So we know that the limit as n goes to infinity of the absolute value of this quotient is less than 1. Okay, so this limit is a finite number, and not only that, it's a number smaller than 1. Certainly it's a non-negative number, right? Because the terms of this sequence if you think about all of this as like a bn for all n, so you can think about bn as being this. So bn is a sequence, and certainly every bn is bigger than or equal to 0, right? Certainly every bn is bigger than or equal to 0. Why? Because it's the absolute value of something, right? So this is a non-negative entity for sure. And the limit, the worse it gets, is to 0, right? So this limit is a number that's non-negative and smaller than 1. Okay. How about we give it a name? How about we call this limit L? So L is smaller than 1 and it's positive, right? Or non-negative. Okay. Now, what do we want? What do we want to show? We want to show that the series is absolutely convergent. And what does it take for a series to be absolutely convergent? It takes the following. You need to show that the series whose terms are the absolute value of the terms of that series an. So you get the series whose terms are absolute value of an is convergent. That's what it takes. This is what we want, right? This is what it means for this series to be absolutely convergent. Okay. All right. So that's what we want. We're going to find that this is a finite number. Okay. All right. Let's start from what we have, and this is the thing that we have. We know that the sequence Bn, remember we just introduced that the Bn to be the absolute value of this quotient. We know that Bn converges to L, correct? And what does it mean that the sequence Bn converges to L? It means that the sequence Bn starts being in any neighborhood of L from a certain rank on, right? So if this is L, this is 0, and this is 1. So no matter what neighborhood you choose of that limit L, you're gonna start finding the sequence Bn from a rank on. Okay, so no matter what neighborhood you take, the sequence is gonna start being here. You know what I'm gonna do? I'm gonna take this upper bound to be a number r, and this r is between L and 1. Okay, so I'm gonna choose, I can certainly choose an r between L and 1. Why? Because L is a number smaller than 1. So there is an opening between L and 1. So as such, choose an r there. I have infinitely many to choose from. Choose one of them and create this neighborhood of L whose upper bound is r. Okay, and keep in mind that r is a number that's between L and 1. Correct? So what do we know about this neighborhood? We know that the sequence Bn is going to start being here from a certain rank on. Correct? So we know that the sequence is going to start being here from a certain rank on. Now what's the sequence I'm talking about? The Bn sequence is going to start being here from any rank, from a certain rank on. Let's call this rank n naught. So from that rank onward, you're going to get this. The Bn's are going to live here, right? Okay, because why? Because the Bn converges to L, and this is what it means. Okay. So thus, there exists a rank n naught such that for any rank bigger than n naught, we have that the absolute value of Bn, right? The Bn starts being there. So what does it mean? The absolute value of Bn, okay, what's absolute value of Bn? This Bn, right? Because Bn is non-negative. So the Bn is going to start being here. So Bn is less than R. Am I correct? So Bn is going to start being here. Okay. All right, and what is Bn again? Bn is that the absolute value of this guy. So I can take Bn out, and I can replace it by the absolute value of that quotient. So the absolute value of an plus 1 divided by an. All right, so far so good. So the sequence Bn is going to start being here, but what's the sequence Bn? This is a notation for this absolute value. All right, so we get this. And what does this mean? What does this mean? What does this mean? Well, this means that an plus 1 in absolute value is less than r times absolute value of an. Let me write it backwards. So absolute value of an times r. Agree with this? Just multiply through by absolute value of an. So this cancels. You get the absolute value of an plus 1 is less than r times the absolute value of an. So we get this. Okay. All right, so what do we have? From this rank onward, from n naught onward, this is going to occur. Let me summarize it in a new line. So for any n greater than or equal to n naught, that's going to happen. That's going to happen. Yes? Very good. So in particular, so no matter what n you give me, how about I do the following for you? How about I'm gonna erase this guy and this guy and this guy, but keep in mind this is the same guy, right? So whoever is gonna be sitting here is gonna sit here, is gonna sit here. Yes? Okay, but keep in mind that the bullet has to be, that brown bullet has to be an integer, right? Okay. So how about we take the bullet to be n naught itself? So therefore, if we take the bullet to be n naught, Certainly n naught is greater than or equal to n naught. So as such, I'm going to be able to write this property. How would you write this property when the bullet is replaced by n naught? We get this. Right? We get this. Okay. How about now we replace the bullet by n naught plus 1? We're going to replace the bullet by n naught plus 1. Certainly n naught plus 1 is bigger than or equal to n naught. We're adding 1 to it. So certainly such a choice validates this, and as such it's going to validate this, because as long as you give me a number bigger than or equal to n naught, you get this, you have this for it. So choose the bullet to be n naught plus 1. This becomes the absolute value of a sub our choice of the bullet, which was n naught plus 1. So the bullet is n naught plus 1 plus another 1, so we get n naught plus 2, less than the absolute value of a sub the choice of the bullet that we have now, which is n naught plus 1, times r. Agree with that? Okay. But now, do you see this? Do you see this inequality? A n naught plus 1 in absolute value is smaller than this entity. So what can we say then about this guy? It's technically multiplying both sides here by r. If you multiply both sides here by r, you get that guy on the left side, and you get this times r on the right side. Keep in mind, r is a positive number, right? R is a positive number. You see the choice of r? It's bigger than L, and L is a positive number, right? Non-negative number. So I'm choosing a positive number for r. As such, if you multiply both sides by r, the inequality sign doesn't change. And if you multiply here by r, you're going to multiply here by r, and this becomes r squared, right? So this becomes smaller than absolute value of a n naught times r squared. Okay. So let me be very clear here. What did I use? If we call this star, I used here star, right? With the bullet being n naught. I used here star with the bullet being what? With the bullet being n naught plus 1. And now if you call this guy asterisk, I used asterisk right here. Correct? Just to be very clear. Okay, so we got that the absolute value of a n naught plus 2 is smaller than the absolute value of a n naught times r squared. Let's keep playing the same game. We're gonna do repeated iteration of star in some sense. How about we keep increasing that bullet? The last one was n naught plus 2. How about now we increase it by 1, n naught plus 3. So this becomes what? For the bullet being n naught plus 3, this becomes the absolute value of a n naught plus 3. Sorry, the last one was n naught plus 1, right? Now it's going to be n naught plus 2. The bullet is n naught plus 2. So absolute value of a n naught plus 2 plus 1 is going to be a n naught plus 3, right? Okay. One more time. I'm replacing the bullet by n naught plus 2. If you do so, certainly n naught plus 2 is bigger than or equal to n naught. If you do so, this becomes absolute value of a n naught plus 2 plus 1. So a sub n naught plus 3. We get this. And this becomes smaller than absolute value of a sub the bullet. The bullet of the choice now is n0 plus 2, right? Times r. Okay. Very good. And now do you have a bound for this? Yeah, it's right there. How about we give it a name? How about double asterisk for a name? So I'm talking technically about this. I'm talking about that guy being smaller than this guy. That's the double asterisk I'm alluding to here. I'm referring to. Okay. So you see the highlighted piece? The absolute value of a n naught plus 2 is smaller than that entity. What do I want? I have the absolute value of a n naught plus 2 times r. So let's multiply both sides by r. Multiply here by r and multiply here by r. This becomes r absolute value of a n naught plus 2, smaller because r is positive, smaller than this times r, which means a n naught, an absolute value, times r cubed. Correct? So we get this. Again, let's be clear. So what did I use? So what did we use here? We used star, and we used here double asterisks for that upper bound. Correct? And let's keep thinking about this. I mean, if we keep doing this, what are we doing? If we keep doing this, we're gonna ultimately have, you can show it by induction, but I'm gonna just write the general case. Look, you see this? The first one, asterisk, absolute value of a n naught plus something is smaller than absolute value of a n naught times r to power that thing. Which thing I'm talking about? That thing here, right? When we had it 2, we got that 2 here, and the rest are the same. So we get smaller than absolute value of a n naught, same thing, times r2, and that 2 is technically this guy. And for the 3, same thing. So it makes it plausible to believe, I mean, even though we can show it. So in general, we can say, so and so on. In general, we have what? That the absolute value of a n naught plus that number, I don't know what you want to call it, I maybe, smaller than absolute value of a n naught times r sub power I. And this is for all I starting from 1 all the way to infinity, right? So for all I in n. Makes sense? So whatever this guy is here, a n naught plus I is an index. Okay, it's part of the index. So n naught plus I is part of the index. Okay, just to be clear on this. Okay, so whatever I is, that I here is gonna sit as a power. I made the first 3 cases. You can keep going, and at least you can show it by induction. Okay, you can show it by induction to see the general case, but it's not that bad. Okay, so we have this. We have this. I'm gonna ask you to think about this series. How about this series? What can we say about this series? Well, a n naught, remember, n naught is a fixed number. Why it's a fixed number? It's the rank. It's the rank that exists. This is a fixed thing here, right? This is a fixed thing. It's a fixed thing when we chose the neighborhood of L, and we chose it that has to do with the R being the upper bound of that neighborhood. So n naught is a known thing. We know it. So a n naught, an absolute value, is a known number. Okay, so I know what this number is, and then r to power I. This looks, the format of this term looks like I mean, this term here looks very close to the terms of geometric series, right? Let's remind ourselves what r is. What is r? R is a number that's positive and smaller than 1. R is a smaller than 1 number. Aha, all right. So this is a geometric series with the common ratio being smaller than 1. So since this is a geometric series, so this is a geometric series with r being smaller than 1, so this is going to be a convergent one. So since this is a geometric series with the common ratio being smaller than 1, R, remember an absolute value, I mean, as long as the common ratio and absolute value is smaller than 1, then the geometric series is a convergent one. Well, here certainly R is an absolute value is less than 1, right? Because in this case, R is positive, so the absolute value of R is R itself. So we have this. So since this is geometric series with R less than 1, it must be convergent. It must be convergent, right? Okay, so these terms, which bound these terms, are terms of a series which converges. And all of these terms actually are positive, right? All of these terms are non-negative, to be more precise. Yes? So I hope this rings a bell. And by this, I'm referring to the direct comparison test. What does it say again? It applies only for positive terms, right? So for those which are not positive, I can throw them away. So make them all positive. Okay, but this is good enough. So remember the direct comparison test? It applies only for positive terms. And it says that if we have a series, let's think about the series who has those terms. So if we have a series whose terms are smaller than those of a known convergent series, in this case, those terms, the geometric series just talked about here, then our series must be a convergent one. So what can we say then? So as such, by the direct comparison test, how about DCT? Direct comparison test. The series an 0 plus I from 1 to infinity, is convergent. Why? Why it's convergent again? Because its terms, what are the terms? These are the terms. They are positive, okay, not negative. Again, you can throw the zeros away and just retain the positive ones. So I can have positive terms of this series, positive terms, and they're all dominated by terms of another series which is convergent. So this is certainly a convergent series by the direct comparison test. Okay. All right. So therefore what? Therefore, this series must be finite, so it's convergent, it's finite. And what is that? What is this series? Isn't it the series as whose terms are absolute value of an, and n starts from n naught plus 1 all the way to infinity? Think about this one. What's the first term of this series? When I is 1, and when I is 1, we have the absolute value of a n naught plus 1, right? So it starts when n, this one here, is n naught plus 1. And it keeps going all the way to infinity. Okay, so you can list the elements of this series and convince yourself that this is exactly that series here. Okay, so therefore this is a series that converges, because we just showed that this guy is a convergent series, but these two are the same, so this is also a convergent one. Makes sense? So if you don't like to write less than infinity, it is convergent. Yes? All right, so I'm going to highlight again what we have. So I have that this guy is convergent. Is it what we want? Is it what we want? Well, what did we want? We wanted that this series to be convergent. What's the difference between this one and what we just showed? Oh, just adding finitely many elements. Just adding 5. So what are we missing from what we want? What are we missing here from what we want? We're only missing the first n naught terms, right? The first n naught terms. So we're missing a1, absolute value of a1 plus the absolute value of a2 plus etc. all the way to the absolute value of a naught. Correct? But if you add finitely many elements to a convergent series, it's going to remain a convergent one. Remember, finite number of terms doesn't affect convergence, right? So therefore, the full series is going to be a convergent one. Why again? Because I'm just adding finitely many elements to a convergent series, or finitely many summands, right? Okay, so we get this as desired. As desired. Okay. So we finished the first part. So we just finished the first part. What's the first part? If this occurs, then the series is absolutely convergent, and we got it. And this is an automatic, this is a consequence, right? Hence, the sequence is convergent, because every absolutely convergent series is convergent. Now, the second part, if the limit of the absolute value of that quotient is bigger than 1, the series must be a divergent one. Okay? So how can we show this? Part 2, the limit as n goes to infinity of the absolute value of n plus 1 over a n. So we know that this is now bigger than 1, right? So this is what we have at this point. And what does it mean? By the way, this guy now is bigger than 1 doesn't mean that it's a finite thing. This may be infinity, right? Infinity is bigger than 1. So what does this mean? This means that there exists some rank, call it big N, such that for any rank after this, that thing is going to be bigger than 1, right? So if you call these terms, if you call this whole thing Bn, as we did before, what does it mean that the limit as n goes to infinity of Bn to be bigger than 1? It means that the terms Bn start being above 1, beyond 1 from a certain rank on. This is exactly what I said. Okay, and what does this mean? This means that there exist n and n such that for any n greater than or equal to n, an plus 1 in absolute value is greater than an, right? If you multiply both sides by absolute value of an, you get this. Make sense? Okay. Therefore, what can we say about this? What can we say about this? Well, certainly this doesn't go to 0. The limit as n goes to infinity of the absolute value of an, certainly this is not 0. Why? Look, let's think otherwise. Let's think otherwise and reach a contradiction. Because otherwise, what do I mean by otherwise? So that is to say, if we assume that this is actually 0, if we assume that this is actually 0, what does it mean to be 0? What does it mean that the sequence absolute value of an converges to 0? It means for every threshold epsilon, there exists a rank n naught that depends on epsilon, right? It's a function of epsilon, natural number, such that for any number bigger than or equal to n naught, this sequence, right? This sequence, absolute value of an, starts being inside any neighborhood of, or starts being inside the epsilon neighborhood of 0, which means this is smaller than epsilon, right? Doesn't that mean this? So again, if the limit of Bn, where Bn is the absolute value of an, is 0, it means that for any threshold epsilon, the sequence Bn starts being inside the neighborhood of radius epsilon. Neighborhood of what? The 0 neighborhood. It's the neighborhood of 0. So it means that the distance separating those terms from 0, which is this, is smaller than epsilon. Make sense? Okay. Well, I'm I'm gonna specialize epsilon to be absolute value of a sub n. What's this capital N that I'm writing here? It's the n I know from from an earlier stage, right? From this earlier stage. So I know the n. Choose that guy, the capital nth term of that absolute value of an sequence, and choose it to be epsilon. As such, you're gonna be able to find me n naught that depends on this choice of the threshold, such that for any number n bigger than or equal to n naught, this is going to be smaller than our choice of epsilon. And what's our choice of epsilon? It's the absolute value of a sub capital N, correct? So since n naught exists, and this happens for any n greater than n naught, okay? How about now we choose an n greater than both capital N and little n naught. So how about choosing n greater than the maximum of those two guys, which means greater than both of them. Okay, if n is greater than both of them, then that's gonna hold for me. I'm technically saying not all of this. I'm technically saying that this is gonna hold for me. Why this is gonna hold for me? Because this holds for any choice of n that's bigger than or equal to capital N. And this n certainly is bigger than capital N. So this is gonna hold for my choice of little n. And what else is gonna hold? This is also gonna hold. This is also gonna hold for me. Why? Because again, this holds for any choice bigger than or equal to n naught. And certainly the n I'm choosing is bigger than or equal to n naught because it's larger than n naught and larger than capital N. So certainly larger than n naught. So both of these are gonna hold for me for this choice of n, right? So do you see the contradiction already? So thus, because of this, I'm gonna be able to write an is less than absolute value of an plus 1, and since n plus 1 is bigger than or equal to n naught, why n plus 1 is bigger than or equal to n naught? Because n itself is larger than n naught. So n plus 1 is going to be larger than n naught plus 1, which in turn is larger than n naught. So I have this inequality that holds for me when n is replaced by n plus 1. So I get that this guy is smaller than the absolute value of an. Correct? So I'm using this property here for the n chosen, and I'm using this property here for n plus 1 instead of n, which because of the choice of little n, I can replace this by n plus 1. Okay, so we get this. All right, back to this one. Remember, this one holds for any choice of n as long as this n is bigger than or equal to capital N. Well, capital N is bigger than or equal to itself. So I can rewrite this when little n is replaced by capital N. So we get that, I'm going to read it backwards. Absolute value of a capital N, is smaller than absolute value of a sub capital N plus 1, right? So I get that this is smaller than the absolute value of a capital N plus 1, right? I'm going to keep applying this over and over. Now for little n to be capital N plus 1. Certainly little n is capital N plus 1 is bigger than or equal to n plus 1. Sorry, certainly n plus 1, capital N plus 1 is bigger than or equal to capital N, right? So I can rewrite this by replacing little n by capital N plus 1. So this becomes absolute value of a sub capital N plus 1 smaller than the absolute value of a sub capital N plus 1 plus 1, so capital N plus 2, right? So I get that this is smaller than absolute value of a sub n plus 2. What's the thing that's smaller than that? It's this guy, because again, repeated application of this. Now with capital N being with little n being capital N plus 1. So this guy becomes N plus 1, this guy becomes capital N plus 2. So we get this. And so on. You're going to keep adding and adding one term at a time. And remember, little n is smaller than capital N. So eventually, if you keep adding from capital N, eventually one at a time, you're going to reach little n. You're going to reach little n. So if you keep doing this game over and over, eventually you're going to reach little n. Make sense? I repeat, that little n is bigger than capital N. And I can, as we said, I can reapplying this over and over and passing to the next term and the absolute value of a n sequence. So here I'm gonna pass from absolute value of a capital N to the next one, which is absolute value of a n plus 1. So a n is gonna be smaller than a sub n plus 1 absolute value, and that term is gonna be smaller than the next one, and then the next one, and so on. And since little n occurs after n, after capital N, eventually, if you keep doing this over and over, at some point you're gonna reach the nth guy, right? You're gonna reach that guy. And now connect the two here. Absolute value of a n is smaller than itself. This is a contradiction, right? This is a contradiction. So this is a contradiction, right? Because something cannot be smaller than itself. And this is the contradiction I was seeking. So this is why the otherwise doesn't happen. So this must happen, okay? So this must happen, make sense? So I repeat, in this little discussion here I assumed that this is not the case. And I ran into a contradiction. As such, this must be the case. All right, so at this point, I know that this is the case. Limit as n goes to infinity of the absolute value of an is not 0. Therefore, what can we say about this then? This should not be 0. Why? Because if this is actually 0 by the continuity of the absolute value, this must also be 0. But that's not the case. That's not the case, right? I know that the limit of the absolute value is not 0, so this cannot be 0 without the absolute value. One more time. Why? Because go back to the section, the first section in this chapter, 9.1, sequences. We know that if xn converges to x and f is continuous at x, then f of xn must converge to f of x, right? This is what we know as n goes to infinity, right? When f is continuous. Take the f to be the absolute value of the absolute value function. Absolute value is continuous at any point, right? In particular at 0. So what do we have here? We have that if an goes to 0, I'm assuming that this is not the case. I'm assuming otherwise happens. If an goes to 0, which means otherwise, and the absolute value is continuous everywhere, in particular at 0, right? The absolute value is continuous at 0. By this theorem that I just mentioned, once you specialize xn to be an, x to be 0, f to be the absolute value, I can infer that the function f, which is the absolute value, so absolute value, acting at xn, what's xn in my case? An, must also go to f of x. Who's f? The absolute value. And who's x? It's the 0. So that's going to go to the absolute value of 0. And what's absolute value of 0? Is 0. So you see, if we assume that this is not holding, which means an go to 0 as n goes to infinity, we get, by continuity of the absolute value function, we get that the absolute value of an also goes to 0, but that's not the case. The absolute value of an doesn't go to 0. Correct? doesn't go to 0. So this would be the contradiction if you assume that this fails. As such, this must hold. All right? I hope this makes sense. Okay, so I'm gonna erase this part. I'm gonna just say here that this is the case by continuity of the absolute value of the absolute value function at 0. Okay, but now since the reason is in the video, you're watching it, so um, I'm not gonna fully explain it because I already did. I think we already did it also in a different video, so I don't want to repeat myself. All right. So then, if you have a series, the series here is an, right? The series is whose terms are an. If you have a series whose terms do not go to 0, what can you say about the series? So it follows that the series must be what? Must be divergent. Must be divergent by which test? By the test for divergence, because the terms do not go to 0. Remember that test? Okay. All right, so this completes the proof of parts 2 and part 1. So we're done with part 2. We just finished it. Part 1 we finished earlier. So we can use the theorem anytime we want. Okay. All right, and as I promised you, I still have a comment that pertains to when the limit of the absolute value of that quotient is actually 1. Well, you cannot conclude anything, because there are cases where this happens for a series which diverges, and there are cases for when this happens for a convergent series. Let me show you one of each. So for example, if you consider the series whose terms are 1 over n squared, this is a p series, right? With p being 2, so this is convergent. So we know that this is convergent. But what happens to this limit in this case? Well, let's take a look. Let's take a look at the absolute value of this quotient. This would be an in our discussion. So an plus 1 would be 1 over n plus 1 squared. I'm replacing n by n plus 1. And downstairs is an, so it's this guy. And then if you play with the, apply some algebraic properties here, you can say that this is equal to n squared divided by n plus 1 squared. So both of these are polynomials of degree 2. And this goes to 1 in this case, as n goes to infinity, right? So this goes to 1 because the leading term and the leading term are going to survive here. So you get n squared over n squared, and that goes to 1 as n goes to infinity. Okay, so this is a case where you have that limit of the absolute value of this quotient equals 1, and this is in the context of a series that converges. Now, that's another series. This is the harmonic series. And if you take a look at the quotient, this ratio, the absolute value of this ratio, you're going to get what's an plus 1. If this is an is 1 over n. You're going to get 1 over n plus 1 divided by an, which is 1 over n. And again, if you play a little bit with algebra here, you're going to get n divided by n plus 1. And that goes to 1 as n goes to infinity. So that's another case when the limit of this ratio is equal to 1, but this time we have that this series is divergent. Okay? So there is no definite conclusion when the limit of the absolute value of this ratio is equal to 1. It may converge, it may diverge. Okay? All right, let's apply this big theorem, the ratio test that we just proved, on different series. So here's the example. Determine whether each of the following series absolutely converges, conditionally converges, or diverges. Remember, absolutely convergent an absolutely convergent series means a series that converges an absolute value, right? And conditionally convergent means that the series with the absolute value diverges, but without the absolute value, it does converge. And or the series is going to be a divergent one. Okay. All right. So let's take a look at part one. We have this series, which is an alternating series. If you try to apply the alternating series test here, you can try and see what happens. I don't think it's going to be an easy game to show that these guys are going to decrease. Okay, but you can try. How about applying the ratio test? So this guy is going to be treated as an. So let's take a look at this ratio, an plus 1 divided by an. If you take a look at this, well, this is, forget about this minus 1 to power n, because the absolute value is going to absorb that guy, right? Because this guy is minus 1 or 1. With the absolute value, it's going to be absorbed. So we're going to have n plus 1 cubed divided by 3 to power n plus 1. Okay, let me take this a little to the top. Okay, and then over, this is the an plus 1 over an, so it's going to be n cubed divided by 3 to power n, right? So we have this ugly looking quotient, but you know, it is what it is. Okay, so then we're going to try to simplify here. We're going to try to simplify. The absolute value here is not doing any job because all the terms are positive, right? So we can drop it. I can keep it, but it's not doing any job. So it's just decoration at this point. So we have then n plus 1 cubed divided by 3 to power n plus 1 divided by n cubed, and the whole that denominator is also part of it is that denominator 3 to power n. And this is the same thing as saying n plus 1 cubed divided by 3 to power n plus 1. And if you're dividing by this quotient, it means you are multiplying by the reciprocal of this quotient, right? So you are multiplying by this, right? Okay. And now if you simplify 3 to power n, what does this mean? 3 to power n plus 1. This only means 3 to power n times 3, right? So this means 3 to power n times 3. And then if you simplify by 3n, 3 to power n, this is gone. So downstairs is simply 3. Downstairs is simply 3. And where does this go? This becomes n plus 1 cubed divided by 3n cubed. And where does this go? As n goes to infinity. Well, as n goes to infinity, this goes to n, this is upstairs is going to behave as n cubed, the leading term, and downstairs is 3n cubed. So this is going to go to 1 over 3. This is going to go to 1 over 3. And 1 over 3 is smaller than 1, right? 1 over 3 is smaller than 1. And the ratio test tells you, let me take you back to the first page of this. The ratio test tells you that if the limit of this ratio is smaller than 1, then the series is absolutely convergent, right? So back to our discussion, the series is absolutely convergent. So hence the series is absolutely convergent. Okay, because the question was, is it absolutely convergent, conditionally convergent, or diverges? In this case, the series is absolutely convergent. Part 2. Now the an looks like this. That's the an term. We're gonna also take a look at the ratio test, the ratio. So we're gonna run the ratio test. All right. Well, an plus 1 here, every n has to be replaced by n plus 1, right? Because this is an. So an plus 1, every n is going to be replaced by n plus 1. So I'm going to have n plus 1 squared times 2 to power 2 times, remember the n has to be replaced by n plus 1. Think about it. N has to be replaced by n plus 1 plus another one. That's n plus 2. That's n plus 2. Divided by 5 to power n plus 1. And divide by an downstairs. So it's an, it's this guy. So n squared times 2 to power 2n plus 1 divided by 5 to power n. Right? So this is the ratio, absolute value of this ratio. All right. The absolute value here is not doing, again, any job. You can simply erase it. You can simply erase it because all the terms are positive here. All the terms are positive. And this is then equal to n plus 1 squared times 2 to power 2 times n plus 2 divided by 5 to power n plus 1. And divided by this quotient means I'm multiplying by the reciprocal of the quotient. And what's the reciprocal of that? What's the reciprocal of that? It's 5n upstairs, and downstairs is n squared times 2 to power 2 times n plus 1. Yes? Okay. Now, if you simplify by 5 to power n, that's going to cancel, exactly as we did above. That's going to be just 5. And if you divide by, what does this mean? 2 to power 2 times n plus 2, and here I have 2 to power 2 times n plus 1. Well, this guy is equal to 2 to power 2n plus 4. Agree with that? 2 to power 2n plus 4. And this guy is equal to 2 to power 2n plus 2. Right? Now if we simplify, the 2n and the 2n guys are going to leave, are going to simplify. Why? Because this means 2 to power 2n times 2 to power 4. Okay, maybe it's better to actually write it this way. So again, this is equal to 2 to power 2n times 2 to power 4, and this means 2 to power 2n times 2 to power 2. Now I hope you see it. If you simplify by 2 to power n, we choose a different color. So if you simplify by 2 to power n, this and this, these are gone. So you get 2 to power 4 divided by 2 squared, and 2 to power 4 divided by 2 squared is simply 4, right? This is 16 divided by 4, so only 4. So we get that this is equal to 4, right? 16 divided by 4 is 4, divided by 5 times n plus 1 squared divided by n squared. Yes? Divided by n squared. So we have this. And where does this go as n goes to infinity? Where does this go as n goes to infinity? Well, as n goes to infinity, the leading term upstairs is n squared, downstairs is n squared, this goes to 1, so the whole thing is going to go to 4 over 5. Okay, and 4 over 5 is smaller than 1. As such, the series is going to be an absolutely convergent series. Okay, so that's going to be an absolutely convergent series. by the ratio test. Okay. All right, part three. So now the terms look like this. This is an, and then by the way, we can rewrite an as 7 to power n over n factorial, right? Remember, n factorial means n is a natural number here. This means 1 times 2 times 3 all the way to n, right? Okay, so agree with that? So this guy, 1 over 7 to power negative n can, negative in the exponent means means the reciprocal, and the reciprocal of 7n is 7n. Okay, so what's the ratio then between the absolute value of an plus 1 and the absolute value of an? What's this ratio? Well, we don't need the bars here because an plus 1 and an are both positive, so no need for bars, right? Because everything is positive. So we get 7 to power n plus 1 divided by n plus 1 factorial divided by 7 to power n divided by n factorial. Yes? And that means 7 to power n plus 1 over n plus 1 factorial. It's just algebra, okay? N times n factorial divided by 7 to power n. Again, because we are dividing by this, which means multiplying by the reciprocal of that. Simplify here. If you simplify 7 to power n plus 1 and 7 to power n, you only get 7 upstairs. And if you simplify n factorial and n plus 1 factorial, it's not hard to see that n plus 1 factorial, what's k factorial if k is a natural number? It means 1 times 2 times 3 times 4 all the way to k. Well, if you have n plus 1 factorial, this means 1 times 2 times 3 times 4 all the way to n plus 1. So I can take the first n guys and combine them, we get n factorial times the last guy, which is n plus 1. Make sense? So what I'm saying is, let me write it here. N plus 1 factorial means 1 times 2 times all the way to n plus 1. So the previous one is going to be n and then n plus 1. Yes? All this guy here is n factorial. So it becomes n factorial times n plus 1. That's what I'm saying here. Okay? All right. So then what? If you simplify by n factorial, we only get n plus 1 downstairs. So this is the absolute value of the ratio. And where does this go as n goes to infinity? As n goes to infinity, where does this one go? Well, as n goes to infinity, this is going to go to 0, right? Because that guy downstairs is going to blow up, and upstairs is 7. It's a pure constant, which is non-zero. Even if that's 0, this whole thing is going to be 0, right? So, long story short, the absolute value of that ratio is going to go to 0 as n goes to infinity, which is smaller than 1. So we still have a series which is an absolutely convergent series. So the series is absolutely convergent by the ratio test. Part 4. So in my context now, this is my an. This is my an, right? If you take the ratio an plus 1 divided by an in absolute value, this is equal to the absolute value of Again, no need for absolute value because everything is positive here. So n to power n is divided by n factorial is an. So if you want to take a look at an plus 1, it's going to be, every n is going to be replaced by n plus 1. We get n plus 1 to power n plus 1 divided by n plus 1 factorial. And downstairs I'm going to have n to power n divided by n factorial, right? Okay. And this means n plus 1 to power n plus 1 divided by n plus 1 factorial times n factorial divided by n to power n. Okay. And same thing as we just did here. N factorial, if you divide n plus 1 factorial by n factorial, you get n plus 1 here. Okay. So since we just did it, allow me to just do it here. If you divide this with this by n factorial, this is going to be 1, and what you're going to be left with here is n plus 1 without the factorial, right? You're going to get just the last part. Okay, and then what do we have? And then we get that this is equal to n plus 1 to power n plus 1 divided by n plus 1 times 1 over n to power n. This is what we have so far, right? This is what we have so far. All right, so I have n plus 1 copies of the factor n plus 1 up downstairs. I have one copy of this. I can simplify by n plus 1, lose one of those guys. So, I mean, this looks a little confusing. Let me explain. Don't worry about what this guy is. It's the same guy. Forget what it is, okay? So I have n plus 1 copies of this guy here, and I have one copy of this guy downstairs. So this looks like a to power n plus 1 divided by a. Now what's a to power n plus 1 divided by a? Isn't it a to power n? So technically you lose one of them, right? You lose one of them. Make sense? Okay, so we get what? We get the following. I forgot to erase that. So that's this is gonna simplify this guy, and then we have n plus 1 to power n divided by n to power n. Yes? Okay. And that guy is equal to the whole thing to power n, right? The whole thing to power n. I'm just playing with algebra here. And this guy is the same as n divided by n, which is 1, plus 1 divided by n. The whole thing to power n. And I hope you start recognizing where this goes. This is the definition of Euler's number as n goes to infinity, right? As n goes to infinity, this is going to Euler's number, to E, as n goes to infinity. Remember, E is about 2.718 and so on. It's an irrational number. So that thing, as n increases, it's going to approach a number E, which is referred to as Euler's number, which is approximately 2.718 or something like this. Okay, what I care about is that this is bigger than 1. This is bigger than 1. The limit is bigger than 1. So since the limit as n goes to infinity of this absolute value of the ratio n plus 1 an is bigger than 1, it's actually E, which is bigger than 1, the series is gonna what? What does the test tell us? Well, it tells us that the series is gonna be a divergent series, right? If the limit of this ratio is bigger than 1, then this is gonna be a divergent series, correct? Okay, so we go back to our page. So this is gonna be a divergent series. The series diverges. By the way, we dealt with um, terms like this before, if you remember. We dealt with terms like this. Let me just make some room for a discussion, another discussion. So this is the end of part 4 using the test. We know that the series is divergent, which is good, okay. But now, since we talked about this before, I just want to remind you. Look, you see an as n to power n divided by n factorial. So alternatively, what can I say? So alternatively, so a different method, different approach. N to power n divided by n factorial. We talked about this, as I mentioned, I think in the sequence section. Well, n to power n is the same as n times n times itself n times, right? So again, how many times? N times. And downstairs, I have n factorial, and n factorial is 1 times 2 times 3 times all the way to n. How many terms from 1 to n? N terms. So the same number of elements here, the same number of copies of n in the numerator, I have the same number of factors downstairs. I mean, the number of factors upstairs and the number of factors downstairs match. Okay. All right. And the way we did it in the other lecture, the other video, what can we say about n over 2? N by design here, because we kept going, right? But because we kept going, n is bigger than 2 or equal to 2, right? Because we kept going and when we wrote the n factorial, so the assumption is n is bigger than 2. So if n is bigger than 2, then n over 2, what can be said about n over 2? Isn't it bigger than or equal to 1? Correct? And similarly, how about this? Isn't it also bigger than 1 or equal to 1? Because we assume that we kept going after 3 all the way to n, and so on and so forth. Each one is going to be bigger than or equal to 1. And even the last one is bigger than or equal to 1. Right? So all this guy, all this block is bigger. I mean, each of the factors in this block is bigger than or equal to 1. So the whole block is bigger than or equal to 1 times 1 times 1 n minus 1 times. So you get that this block is at least 1. So this block is at least 1 times n is going to be at least n then. Right? So that's going to be at least n. Okay? So this is an, this is an. That guy is an. So an is equal to this quotient, and which in turn is bigger than or equal to n. Now, as n goes to infinity, I mean, an is bigger than or equal to n for all n, right? For all n, I should say. So I get that an is bigger than or equal to n for all n. Now, if n goes to infinity, that guy is going to blow up, and an has to also go to infinity, right? Makes sense? So one more time, an here, let me summarize it for you by writing it here. An, what we've seen, an is bigger than or equal to n for all natural numbers n. Correct? Because of this, the higher the n is, the higher the an is. If you keep increasing n, if you let n go to infinity, that guy is gonna blow up. And this guy is at least this much that also have to blow up. Agree with that? So the an go to infinity as n goes to infinity, because it's bounded below by something that blows up. I hope it's making sense. But all what I care about is that the ans are not going to 0. So the ans are not going to 0. They're blowing up. And if they're not going to zero, what happens to the series whose terms are those guys? It has to diverge by the test for divergence. Okay. So so how about I cram it here? So this is what I have. Then the limit as n goes to infinity, an is going to be plus infinity, which is certainly not zero, and hence the series is going to diverge. Okay. So we could have discussed it via a different approach, a couple of lines, instead of running the ratio test. But I mean, both approaches obviously they have to yield the same result. All right, number 5, the last problem in this set of problems. This is an alternating series, and since we're running ratio test, let's run it again. So this is an, this is an. So an plus 1 over an, the absolute value of this quotient is equal to the absolute value of minus 1 to power n plus 1 square root of n plus 1 divided by n plus 2 here, right? Because if you replace n by n plus 1, this becomes n plus 1 plus 1, so n plus 2. And the whole thing is divided by minus 1 to power n square root of n divided by n plus 1. Okay? And minus 1 to power n plus 1 divided by minus 1 to power n with the absolute value. This is gone. No more of these guys, the minus signs. And then we only have the other pieces, which are all positive. So we get square root of n plus 1 over n plus 2 times n plus 1 over square root of n, which goes to 1 as n goes to infinity. So the limit of the absolute value of this ratio goes to 1, and as such, the ratio test doesn't tell us anything. It's inconclusive, right? Remember the comment after the test? So we are on our own. The test doesn't produce anything, doesn't tell us anything. All right, so we gotta do something else. We gotta do something else. What should we do? Okay, so how about, this is an alternating series, right? This is an alternating series. How about we use the alternating series test? Okay, how about we use the alternating series test? So we instead use the alternating series test. Let's abbreviate it. Let's take the acronym AST. Okay, let's remind ourselves what the alternating series tests say. It says that if you have a series that look like this, minus 1 times terms, and if you happen to have that these terms decreasing to 0, then the series is going to be a convergent series. Correct? So let's make the case that the square root of n over n plus 1 is a decreasing sequence. So the sequence square root of n over n plus 1 decreases, this is our claim, decreases to 0. Okay, this is a claim. We need to talk about it. Okay. Well, this goes to 0. Okay, it's not a big deal to show that this is going to 0. I mean, the leading term upstairs is n to power half, and the leading term downstairs is n. This is the same as the limit as n goes to infinity of 1 over n to power half, which is 0. So this is not a problem. How about the decreasing? So how about we consider the function f of x to be square root of x divided by x plus 1 on 1 to infinity. And how about I leave it as an exercise that f is a decreasing function on 1 to infinity, okay? And as such, if you show that this is a decreasing function, those terms which belong to, I mean, f of n, if n is an integer, is going to be a n. It's going to be not a n. It's going to be this term, right? Square root of n divided by n plus 1. So show that this is a decreasing thing, and realize that those terms are part of this. They are output through this function f. And since this is decreasing, those terms also must be decreasing, and hence the sequences. Okay, so left as an exercise, and this is gonna be decreasing. Okay, this is gonna be decreasing, and as such, the sequence square root of n divided by n plus 1 is decreasing. And decreasing to where? It's decreasing to 0, as we said. Its limit is 0. Okay? So the AST, thus by the AST, and what's AST? It's the alternating series test. The series is going to be divergent, right? It's convergent, sorry. It's convergent. Agree with that? All right. But this is not the question. The question is it, if we remember the question correctly, the question was, is it absolutely convergent, conditionally convergent, or divergent? So far, definitely it's not a divergent, so this is out of the door. The only remaining two are either it's going to be absolutely convergent or conditionally convergent. Conditionally convergent, remember, it's convergent without the absolute value, but with the absolute value is going to diverge, correct? Okay. So how about we take the absolute value and see what happens? So is that series absolutely convergent? Is the series absolutely convergent? I'm checking, I'm asking, right? So that is to say, is or does this series with the absolute value values of the terms of that original series, which is the same as the series here. I mean, the only thing that's absorbed by the absolute value is the minus 1 to power n. So we get this. So does this converge? Right? Does this converge? So these questions are the same. If the series is absolutely convergent, then if you put the bars here, I should get it to converge. And how about we use the limit comparison test to compare it to another series, which is what? Square root of n, 1 over square root of n. Okay, because look, this guy, the leading term here is square root of n divided by n, and if you take this ratio, this is n to power half downstairs. We talked about this before. So we use the limit comparison test, LCT, to compare the series, this one, with this one here, and 1 over square root of n. Okay, remember what that test says? What does it say? It says certainly both of the series have to be positive terms, and if you take the limit of the ratio of the terms as n goes to infinity, and you get a number that's finite and positive, then the two series are going to have the same nature. Okay, they're going to have the same nature. So let's take a look. Let n go to infinity, and let's take the quotient between square root of n over n plus 1. So the terms of this series divide by the terms, or the nth term of this series. Okay, and by design, I mean, we chose this so that at the limit they match. This is going to be 1. Okay, reconvince yourself that this is actually 1. And certainly this is a number that's positive and finite. As such, the two series are going to have the same nature, are of the same nature. And what's the nature of this series? What's the nature of this series? Is it convergent or divergent series? This is a divergent series. Why? Because this is a p series with p being half. So this is divergent since it's a series, it's a p series with p being half, which is smaller than 1. And we know for those p's, the series is divergent, correct? So since the two series are of the same nature by the limit comparison test, that thing is gonna also be divergent. So then this is gonna be divergent. Okay, so let's sum up. So to answer this question, is the series absolutely convergent? Meaning with the absolute values, does it converge? We checked, it doesn't, because with the absolute value, it turns to be this one, which is of the same nature as the p series with p equals half, which diverges. So with the absolute value, the series is going to be a divergent series. As such, without the absolute value, it converges. With the absolute value, it diverges. So the series is going to be, so all in all, the series, the initial series without the absolute value is conditionally convergent, right? It's conditionally convergent, meaning it converges without the absolute value, but it diverges with the absolute value. Okay. All right. The next test, which is convenient to apply when nth power occur. Let's read the theorem. By the way, the proof of this theorem, I'm going to leave it as an exercise. Okay, it's mentioned here because it's very, very, very similar to the ratio test. Okay, so let's read the root test. If the limit as n goes to infinity of the nth root of the absolute value of an is less than 1, then the series is absolutely convergent, and as such, it must be convergent, because every absolutely convergent series is convergent. And if the limit of that nth root of that guy is going to be bigger than 1, then it must be a divergent series. Okay. As I mentioned, the proof is very, very similar to the ratio test. I encourage you to do it. There's a small tweak, and then the whole thing is gonna be the same. All right, the comment, very much as before. If you have 1 as opposed to smaller or bigger than 1, the test is gonna be inconclusive. Okay, the series may diverge or it may converge. Can you actually find examples like this? Can you find one that verifies this, that the limit of the nth root of the absolute value of an equals 1, where it's going to converge, and 1 with the same condition where it's going to diverge? Try to construct an example with this. Moreover, if you go to what this comment is saying, if you go to the ratio test and you get that the test is inconclusive, meaning that the limit of this ratio is 1, no need to do the root test, which is the test just mentioned above. No need to do it, because this is going to also be inconclusive, which means the limit of this guy is going to be also 1, and vice versa. If the root test is inconclusive, certainly the ratio test is going to be also inconclusive. And here's a question. Can you actually explain why this phenomenon is occurring? Think about this, please. And ask me if you obviously have questions. Okay. So let's answer this question. Determine if the series is absolutely convergent or conditionally convergent or divergent. Look at the nth term here. Look at the nth term here. This is an, right? Look at this guy. This looks like the nth root of something, right? So, and the root test is made for these guys. So look, the next test is convenient to apply when nth powers occur. Because you take the nth root of the absolute value of the nth term. So if an has an nth power, which is the case here, then that test is gonna get rid of that n, and it's gonna give us some useful information. Let's run it. So we get limit as n goes to infinity of the nth root of absolute value of an. This is the limit as n goes to infinity. The nth root of the absolute value of an to power n, the n and n. Okay, let's do it in stages. So the nth root of the absolute value of that guy, but the absolute value of an is an itself. So we have 2n plus 3 divided by 3n plus 2 to power n, because this is a positive entity. And the nth root of the nth power, they undo each other. We get the absolute value of this if n is even, and without the absolute value of this if n is odd. But in this case, n goes to infinity and the base is positive, so they undo each other in a clean fashion. So this is going to be the limit as n goes to infinity of 2n plus 3 divided by 3n plus 2, and this is 2 over 3, right? Which is less than 1, which is less than 1. So the series is by the root test, the series is absolutely convergent. Yes? Okay. And finally this one. In this case, this term is my an. And look, every guy here has an nth power, right? So it's not hard to see that an is actually pi cubed divided by e to power 5 divide by n, so times n downstairs. The whole thing is to power n, right? So it's not hard to see that this is the case. And if you run the root test, we're gonna have to take the limit of this guy, which is the n with the nth power, they undo each other. We get the limit as n goes to infinity of pi cubed divided by e to power 5n, which is 0, right? Which is 0. So which is 0, which is less than 1, and as such, the series is absolutely convergent. The series is absolutely convergent by the root test. Correct? All right, so this is the end of this section.